Okay, good morning, everyone. We're going to continue today our discussion on palladium cross-catalyzed reactions. And look, last week we looked at two coupling reactions. We looked at Heck coupling, Heck-Mitsunoki coupling, and we looked at Suzuki coupling, and we also had some tasks associated with us. And can someone remind me what is a Heck coupling? When we couple ones, for example. Correct. Alkene, for example, an aryl halide, but you can also do alkene-alkene coupling. Most of this coupling chemistry involves sp2-sp2 coupling, right? And it's usually exemplified by using aryl groups. Now, in the Heck coupling cycle, remember, we didn't really have a transmetallation. The mechanism was slightly different. But for the rest of the coupling reactions, including the Suzuki coupling that we discussed last week, we have generally a sequence oxidative addition, transmetallation, reductive elimination. So we're going to continue this today. And the first sort of variation on the theme is the so-called Negishi coupling we're going to look at. The story is the same. The story is the same as with Suzuki coupling, except we employ a different transmethylating reagent, and in this case the transmethylating reagent is a zinc reagent. So let's have a look at the cycle. Again, we start with a palladium 0 species, typically could be generated in situ. Remember we said last week that you can start with a palladium 2 species and then in situ, by adding an appropriate base, generates the palladium 0 active catalyst. Or you can just use a palladium 0 species, for example, tetrachus triphenylphosphine palladium 0, which is a classic example. And basically what we do in this reaction is, again, we couple, for example, an aryl and an alkene halide, or an aryl-aryl coupling. There's a very large, broad spectrum of things that you can actually couple. But again, it comes down to sp2-sp2 coupling. The first step, oxidative addition of the aryl halide or the alkene halide, for example. And then we have this intermediate here. This is obviously palladium 2. And then we do a transmetallation with a zinc reagent. Now, this is really the only variation. With the Suzuki coupling, remember we do the transmetallation with a boron-containing reagent, which essentially reacts with the base first. Here we're doing the transmetallation simply with a zinc reagent. So this is a zinc, X is a halide, R is, for example, an aryl group, an alkene group. The thing that we want to couple to the red R here, basically you have a simple transmetallation, RR, reductive elimination, and you close the cycle. So this is a very versatile reaction, and actually, of course, the question is, why would you use this and not Suzuki coupling or Heck coupling? Well, it really, again, it's just an extra tool that a synthetic chemist has at their disposal. It might, for example, be easier to access, let's say, an aryl zinc halide reagent than it is to make that what we use typically as the transmethylating reagents in the Suzuki coupling, the boronic acid reagents. It really depends. But it's just a variation on the theme, essentially, and it's an enormously useful reaction. Now, here's an example where Negishi coupling is employed in the synthesis of this natural product. This is, in fact, a polyketide that is used by microtubules, right, which are structures in the cell which essentially contribute to the stability of the cell. They have many uses, these structures. And this is one of the things required in the synthesis in a cell of a microtubule, so it's a natural product. And it's possible to access it by doing a very elegant Negishi coupling. So what we have is, if we want to try and couple these two building blocks here to form the a key intermediate in the synthesis of this polyketide, is what these guys have done is basically, you see, you've made a zinc reagent, 310, which is a requirement for this coupling. Remember, we have a zinc X or Z-diaryl or ZX aryl or ZX alkyl reagents, all sorts of possibilities. And check it out. Here's our sp2 halide, right? So that's going to do the oxidative addition in the first step. This guy's going to do the transmethylation, and following reductive elimination, you're going to get the coupling between this and this. So this is sort of the zinc reagent that they employed. So you can see those are the reactions to make such a zinc reagent. Zinc alkyl systems are quite sensitive, right? So they're quite difficult to handle in a laboratory. You have to work under, of course, inert conditions, because they're susceptible to hydrolysis. But obviously, in this case, it worked for them. You can see the reaction conditions going from this iodide precursor to the transmethylating reagent in this coupling reaction employs tertiary butyl lithium. Again, that's not a very nice reagent to work with. It's extremely reactive and burns on contact with air. So quite a dangerous reagent there. But anyway, that's an example where one can employ this so-called Negishi coupling. The next sort of coupling that we have is called Stiller coupling. And this is, again, the same story, just decorated or dressed up, you know, in a different outfit, if you will. This time, instead of using, like we did previously, a boronic acid transmethylating reagent in Suzuki coupling, or what we just saw in Negishi coupling, a zinc alkyl or aryl halide, or even a zinc diaryl or dialkyl, all sorts of possibilities, transfer reagents, or methylating reagents in the Negishi coupling. Instead of coupling, the transmethylating reagent is a zinc 4 reagent. The story is the same, okay? We start off again with typically palladium 0. We have oxidative addition in the first step, which is always the case in these reactions. And the transmethylation in a Stiller type coupling occurs from a zinc 4 reagent. So for what we typically use is a zinc butyl, N-butyl, also a zinc trialkyl or zinc trialkyl R1, something like this. Sorry, tin. Did I say zinc?
Yes.
See, I was still thinking about the previous coupling. It's early in the morning. So this is a typical Stiller type reagent. So an N-butyl, a tris-butyl tin R. Now you can see that the tin here is oxidation state +4. These reagents are actually quite stable. They're a little bit moisture sensitive, but you can sort of handle them. They're quite robust. And what we're doing in a Stiller coupling is we're using that guy as the transmethylating reagents, and we're actually affecting the coupling. So the cycle is the same. We have this transmethylation, right, with this tin reagent. The tin reagent then picks up the X. The R group that's on this tin reagent goes onto the palladium. Now it so happens that what you often have, of course, is that you will have a trans arrangement then of these two R groups that you're trying to couple. So an isomerization step is necessary, because remember we said that reductive elimination can only occur if the two groups that are reductively eliminating are cis relative to each other, right? So that's precisely what I'm representing here. So we have a cis-trans isomerization and reductive elimination, yes.
With this one, there's a separate step for that, but with the Negishi one, you can in one step the transmethylation in the cis-trans.
Yes, I haven't represented that intermediate here. Well, what I've done here is I've represented it as them being mutually cis. So yes, what I've actually done here is I've included that additional step. So typically what you would have, well, you could have, it depends on the systems, right? It depends on steric demand and stuff like that. But what you would typically, what you could have is the transmetallation, that the two groups are mutually trans to each other. Then they need to undergo a cis-trans isomerization and then reductive elimination. So that is sometimes a step. In fact, it is an implicit step that you have in these cycles as well, which I haven't included here. Now, Stiller coupling is a very versatile synthetic tool for chemists, and actually this is a very nice review article. This picture is taken from this review article. It was discovered about 40 years ago, right? So a lot of these coupling reactions we see taking place in the 1960s, 1970s, up until the present day, and variations thereof. This is the article that I was telling you about. Actually, this was published last year, so as you can see, it's nearly 40 years old, this coupling reaction. And the interesting thing about the Stiller reaction, I mean, I've represented here a sort of a generic reaction profile or catalytic cycle that we're familiar with the usual steps: ligand dissociation, access of a hot, catalytically active intermediate, oxidative addition, transmetallation, reductive elimination. But people have studied, here it's represented again, people have studied this reaction in some detail. This is taken from this review. And of course, things are not as simple as they seem. What we have in a Stiller coupling are several possibilities, right? So we have, as you can see here, sort of this open cycle that it's called, a cyclic cycle and an ionic cycle. This is not too important, right? I think for the purposes of this course, keeping things general in terms of that catalytic cycle I just presented suffices. I just present this to show you that people do detailed mechanistic studies to really understand what's going on. And for example, one possibility in a Stiller type coupling, if we look at the cyclic cycle, is that you have the oxidative addition in the first step and isomerization to trans. And then you have the transmetallation with this tin reagent. You see that's butyl-3 tin. That's the classic Stiller reagent, and then you decorate it with some R group here of your choice. And basically what happens is you can think that the carbon atom of this tin group actually sort of interacts with the palladium, generating a planar system like this. And then the tin and the tributyl tin and the halide see each other, and they sort of associate, and you get the product. So that's one possibility. Another possibility is that it follows an ionic mechanism, right? And so on. So there's, people don't just dream these things up. They have experimental evidence for intermediates. Maybe they can view them spectroscopically, you know, at low temperatures using things like nuclear magnetic resonance or infrared. So they have support for these intermediates, and it's very often also supported by the density functional theory calculation. Just one final look at the reaction again, just so that we really pin this down. We start with palladium 0, oxidative addition, transmetallation, reductive elimination. You see again here I've included the cis-trans isomerization step in 1. It's not so important, that step. It just sometimes happens depending on the nature of the substituents. And we go from palladium 0 to palladium 2. Again, we have a broad spectrum of things that we can couple, right? And so that makes this a very useful tool indeed. So Stiller coupling, a very useful tool in our repertoire of coupling reactions. And here is an example where it has been employed in the synthesis of a compound called rapamycin. Rapamycin is actually an agent that is used to minimize the effects of organ transplant rejection. So a very important compound from a, let's say, medical perspective. And what they've done here is a sort of a intramolecular Stiller coupling, a cascade Stiller coupling, where we've in fact done two Stiller couplings using this reagent here. So again, we start off with two sp2 centers. You see, a lot of students think you always start off with an aryl halide in these couplings. It doesn't have to be an aryl halide. Actually, it just has to be an sp2 halide. And as you can see here, it's an alkene halide, right? So that's these two guys are going to then, of course, both of them do an oxidative addition over the palladium 0. Then this tin reagent is going to come along and we're going to have the coupling taking place and we're going to close up the ring. Now, do you see that we could have in fact also done that exact same reaction using another coupling that we've used? For example, well, any one of them, heck coupling. Perhaps if you take this guy, you just react it with ethylene. Remember the hex system, alkene plus sp2 halide, maybe it would work as well. They happen to use Stiller coupling. You know, we could have also employed Nagishi coupling or Gumada coupling and so on. So you see, it really depends on the situation and the availability of starting materials. Again, you see they add a base here because the catalyst precursor is palladium 2. So of course the catalytically active species is palladium 0, which is generated in situ by reaction with this base. So of course to construct this precursor here requires obviously a lot of other synthetic work, but the key step again is this coupling reaction. Kumada coupling, another variation on the theme. You can do this with nickel as well, nickel or palladium. A lot of these coupling reactions in fact work also with nickel reagents. And same story as before. The only thing is in Kumada coupling, instead of using like we did, it's the choice of the transmethylating reagents ultimately. And here we use a Grignard. So it's the Grignard that's doing the transmethylation, cis trans isomerization, reductive elimination. Same story as before. Again, why would you want to do this? Well, it's just another tool that you have in your toolbox. Maybe you know, you have experience in making Grignard reagents and you don't like working with zinc compounds. It all depends, right? But again, it's the same story, just dressed up in a different outfit. Any questions? Lots of coupling reactions.
But so in this case also the catalyst changes, or can we...
Sorry?
In this case also the catalyst changes, or can we use it also with
You can use it with palladium.
palladium as well?
This is just an alternative that also works. This is a nickel bearing a chelate in phosphine, or you can start with palladium 0. Now I want to introduce, so these couplings that we've discussed all up until now is essentially involving sp2-sp2 coupling. We start with an aryl halide, we couple it to a vinyl or an aryl halide. Or, so we can do aryl coupling, we can do alkene coupling. That's what we're doing. sp2-sp2 coupling with one of the 4 variations on the theme that we've looked at. Now I want to introduce another interesting coupling which is slightly different. Here we're doing sp2-sp coupling. So we're coupling, in this case, alkynes to sp2 halide centers. Now that's that's different, because up until now we've done a lot of sp2 coupling, right? And now we're doing sp2 coupling. All right, and this is what Sonogashira coupling is all about. It only works with terminal alkynes, meaning that you require a CH group, and again, it's mediated by palladium 0, that's the active catalyst species. Here basically are the 2 variations. You can have an aryl X or vinyl X coupling with, in both cases, with a terminal alkyne. What you require in this reaction, in addition to the palladium precursor, however, is a co-catalyst. And the co-catalyst that one employs is copper-1 iodide. Doesn't have to be copper-1 iodide, but it must be some sort of a copper-1 species, and you'll see why in a moment when we look at the catalyst cycle. So what's happening in Sonogashira coupling? Here is the cycle, same story as before. We start off, let's say, with tetrachus, triphenylphosphine palladium, we lose some ligands to generate the hot active species. We have the oxidative addition. Now, remember, we tried to couple a terminal alkyne somehow with this R group that we've introduced in this oxidative addition step. But we have to somehow activate the alkyne, right? And how do we do that? This is where the copper comes in, the co-catalyst. The alkyne, in the presence of a base, so it's base mediated, reacts with the copper 1 halide, could be iodide, chloride, doesn't matter, and you form a pretty reactive copper acetylide intermediate. So this is a methylated alkyne, okay? And what that guy then does, right, it acts as the transmethylating reagent. So what you're actually doing in a Sonogashira coupling is you're in situ generating the methylating reagent by reaction with a copper 1 intermediate, or a copper 1 co-catalyst in the presence of a base. And that's how you install the alkyne group onto the palladium. Then you have cis-trans isomerization, if required, reductive elimination of the coupled alkyne. Now that's a very useful thing, right? You can install alkyne functionalities onto aryl rings, or you can couple alkynes with alkenes. Very useful, right? I actually know someone who was doing this sort of research in Berlin, and he made a whole lot of these. Well, he made a new catalyst system, but basically these reactions are very easy to carry out. You throw everything together, you cook it overnight, and you come back the next day, and if you've got a good catalyst, essentially quantitative yields of these coupled products, right? So in Sonogashira coupling, slightly different from the other couplings we've looked at, we're coupling SP and SP2, okay? The other couplings, all of them, from Heck up until Kumada, was SP2-SP2 coupling, in a nutshell, okay? And yeah, so that's Sonogashira coupling. Lots of uses, and I just, again, want to draw your attention to this very important step over here, which is the alkyne, the terminal alkyne activation and subsequent transmethylation with the in situ generated palladium species. And of course, there's experimental evidence for all of these things, right? So this is just to sort of showcase some examples, right? You start off here, again, you can start off for the sake of convenience with the palladium-2 species, which is then in situ reduced by the base to palladium-0. And here you see some examples of coupling reactions. Here we have an alkyne coupling to an aryl halide, works quantitatively. You can even couple, which I think is very interesting, you can do a double coupling. So for example, if you take acetylene, which has of course got a CH and SPCH on both sides of the acetylene, you can in fact do a double coupling with two quantities of aryl and make compounds like this. Classic example is diphenylacetylene, right? So if you take phenyl bromide and you bubble acetylene gas through it, in the presence of copper 1 and tetrakis triphenylphosphine palladium, you're going to get diphenylacetylene, just like that. And again, this is not trivial, right? To do these sorts of reactions with classical organic chemistry is quite difficult. I mean, I don't actually know of a reaction where you can couple, because I'm not an organic chemist, but I don't know of a reaction where you can actually couple an alkyne and an aryl group in one synthetic step, right? And of course, these intermediates are important building blocks for later synthesis, because if you think about it, if you're trying to synthesize some amazing natural product, and you build a molecule, you start building functionalities like that into the synthetic sequence, it opens up possibilities to functionalize it later on in the synthetic pathway. You can, for example, there you've got a CC double bond. You know, in this example here, you could, for example, think of doing stuff like alkene metathesis. You've linked up an alkyne with, let's say, some substrate, which you can do alkyne metathesis with, right? And so it opens up the possibility in modern organic synthesis to do stuff. And that's what I really want us to do in this course. I want us to remember that these are tools, and I want us to see the bigger picture and sort of incorporate them all into thinking about multi-step organic synthesis in a new way. This is just another example to show that in fact you can also do Sonogashira coupling. Interesting. Doesn't have to be with homogeneous systems. You can actually just take a palladium surface, palladium nanoparticles, and that also works. So this is pretty recent work. And actually, you can take palladium nanoparticles or palladium, carbide, which is what you use for hydrogenation reactions. And if you throw in some phosphine, in the top example, you can actually do the Sonogashira coupling, but you can also, just with the palladium nanoparticle, which I find quite interesting, in the presence of copper, so there should be some copper here, do the coupling reaction. So let's revisit everything that we've discussed in the last 2 weeks. We have HEC, we have Sonogashira coupling. Okay, well let's start with sp2, sp2. Let's write them down, okay? Because it's a lot of stuff. So we have HEC coupling, Kumada, Stella, Negishi. What else?
Suzuki.
Huh?
Suzuki.
Suzuki. And Sonogashira. So we've looked at 6 coupling reactions. Now let's just sort of put this into some sort of a conceptual framework, otherwise we're going to go crazy. Basically, HEC coupling stands a little bit on its own, because remember, in the catalyst cycle there's no transmetallation step. It sort of works a bit differently. But what can we do with HEC coupling? It's sp2 coupling, essentially. Example is aryl coupling, aryl alkene coupling, alkene coupling. Kumada, Stella, Negishi, and Suzuki sort of are similar in the sense that it's also sp2 coupling, but the only difference effectively in all of these different couplings is what? The transmetallation reagents. Essentially the same, only difference, and I'm sort of stripping this down. I mean, there are some mechanistic differences like we just saw with the Stella coupling, but if you strip it down to basic fundamentals, it's essentially the same, only the choice of the transmetalliting reagent different. And the third reaction we just looked at now, Sonogashira coupling, where we're doing something slightly different. We're not doing sp2 coupling, we're doing sp2 sp coupling. And it works with terminal alkynes, and we require a copper co-catalyst to activate that alkyne and in situ generate the transmetallating reagent. So you now have a lot of tools at your disposal to build fabulous molecules, right? And this is where a person can start being extremely creative in designing a synthesis for making a fabulous molecule, right? Yes?
In the Sonogashira, can we use other co-catalysts rather than the copper one, or it's just?
No, I mean, people classically use copper 1. You could use, I think you could use other activating reagents. I'm sure people have done that, but typically one uses copper 1.
Is there something specific about copper that makes a good co-catalyst?
I think it's because it's just the right metal for activating that alkyne, right? And making it reactive enough to act as a decent transmetallating reagent. So I think you have to use copper because you have this highly electron-rich CH3004 bond, right? And if you generate a minus charge on that carbon atom, you know, it's kind of really a hot potato. So the copper sort of tames it a bit, right? So yeah, and one can also think about it in terms of hard-soft interactions, right? Because that's quite a soft nucleophile, so it needs a soft metal like copper. I'm sure you could do it with silver as well. It's just not, of course, as cheap as copper. And it's copper 1, right? You need copper 1, which incidentally is not such a stable oxidation state of copper. Copper 2 is more stable. But, I mean, copper 1 is, you can even handle it in air for short periods. It's pretty okay. It's pretty stable. All right, so we've got a whole, we're building up a toolbox, right? We've done a lot of different reactions up until now. And what I want us to do now is I want us to apply some of these CC coupling reactions again in multi-step synthesis. And so think about this, right? You've done organic chemistry as well, so try and combine what you've learned in organic chemistry with what you've learned in catalysis, right? Because that's sort of where we're going. We're trying to design a modern and highly innovative synthetic routes to making molecules. All right, so let's do an example. We did a bit of this last week, but I really think that this is, the nice thing about this is we're at a point now in chemistry where there's not just one right answer, and there is room to be creative in a synthesis. The art of synthesis is designing elegant synthetic routes, okay? So let's do an example. All right, there's kind of a, that is a benzene ring with, well, let's make it a little bit more complicated. All right, that's the target compound, okay? That's the target compound, and I want you to prepare this from easily available starting materials. That guy, and this guy. Those are the two starting materials you must use in your synthesis. Let's do that. How do we proceed? Let's be creative. There's lots of things you could do. Can you see, Nicole?
Yeah.
And I mean, again, if you remember way back when classic aromatic substitution chemistry in classic organic synthesis, you have to use stuff like Field-Crafts alkylation, which is not very, you know, you have all these problems with selectivity in terms of ortho and meta-directing effects and stuff like that. And we can overcome all of that using catalysis. That's the beauty of this. So let's see, what can we do? Does someone have an idea?
Couple the two rings first.
Sorry?
You can couple the two rings first.
Couple
two
two-
rings.
Okay, couple one of the aryl rings first. How?
For using Suzuki coupling with the aryl boron, so you put the boron, right?
So you decide to use Suzuki. So the first step you guys want to do is do one aryl coupling here. All right. So how do we do that? We want to use Suzuki coupling.
Yes.
How do we use Suzuki coupling?
First, you need to turn the aryl halide to a boronic acid.
Correct. So let's do that. So we would basically take something like this, and we'd react it with a Grignard reagent, for example. Then we would get something like this. We would get something like this, which can then readily be converted by a deprotection step to a boronic acid coupling partner. Alright, so we've constructed that guy. So you want to do a Suzuki coupling. So what's the next step? Well, we can take this guy and we can react it. So we must be very careful with controlling the stoichiometry. There might be issues with the selectivity. You might end up with some dicoupled products. But let's suppose if we do the reactions under very carefully controlled reaction conditions, given the symmetry in the molecule, we might be lucky and have a high selectivity to a monocoupled product. So if we take that guy and we react it with the starting material, which is this guy, and we do a Suzuki coupling, using, for example, palladium 0, CHE3004, right? And remember, we need a base. What base would you employ? Anyone will do. Classic example, remember sodium methoxide, for example. So what Suzuki used, one of the bases, or remember the joke, sodium CH3 cook. Right, will do. It's a base. You need the base, remember, because remember the base reacts with a boronic acid in situ and converts it to a borate, which primes it then to do the transmetallation. All right, and if we're very lucky, we will get, selectivity may be an issue, but if we're lucky, we will get the coupled product. So that's a good first step. What do we do now? So we've put the aryl ring on. This is a 1,6. This is hex 1,6. Sorry, 1,5 diene. Yes, it's a hex diene. That's what we have available. So what sort of coupling are we going to do? Heck coupling. Remember, we can do heck coupling with alkenes and sp2 halide centers. So let's do a heck coupling. Heck, right? Heck Mitsuoki coupling. What catalyst are we going to use? Palladium 0 or palladium 2. Remember, we can use palladium acetate. Let's use palladium acetate. Why not? And we need a base. CH3 cook will do. Right? Or let's just write down base. And we should get, with high selectivity, if we're lucky, this guy. Yes. So we've coupled there's 6 carbons here. Remember, in heck coupling, you sort of lock them on together. So there's the hex diene, which is not coupled to the aryl ring. All right, what do we do now? We want to get the aldehyde on. So what are we going to do?
Hydroformylation.
Sorry?
Hydroformylation.
We're going to do hydroformylation. How? We're going to select a catalyst that exhibits a high N2-iso selectivity because we want to install an aldehyde on the end. Remember? We have some, so for example, if we were to use COH-CO4, that doesn't have a particularly high N2-iso ratio, so we need a catalyst that has a high N2-iso ratio. So remember that lecture on Tolman-Cole angles and stuff, cone angles and stuff like that. We would probably pick a rhodium catalyst. So we would do hydroformylation. I would pick RHH EPH3 2CO. Let me just think a moment. There's a 3, sorry, this is a 3 and this is, yeah, that's the correct catalyst. And we would use syngas and 50 bar pressure, hydroformylation. Okay, hydroformylation. So what would the product of that be? Everyone agree. We could have problems with N-to-iso selectivity. That's why we have to carefully select a catalyst that we know steers towards a high N ratio, which is fine because we know how to steer the N-to-iso selectivity using the Coleman-Tolman cone angle of phosphines, and we saw the effect that that has on selectivity. Coleman, by the way, is another scientist as well that I know. That's why I confused Tolman, cone angle, Coleman. Anyway. And what's the final step?
Hydrogenation.
Hydrogenation, yes. Hydrogenation. What would you use? Well, we must be careful that we don't hydrogenate the aldehyde, because those are also prone to hydrogenation. So one could do something very elegant. You could do a hydrogenation, but you might run the risk of hydrogenating the ketone. So what could we do? What could we do
But don't you
instead?
have like those poison catalysts? I don't remember the one we did in organic.
It's called Lindlar.
Yeah, that one.
Lindlar hydrogenation. Yes, that would work potentially because it's a poison catalyst, so it reduces the activity of hydrogenation. But what could we employ in addition? A completely different type of hydrosilylation. Well, you know what we could in fact do? We could protect the ketone and then do the hydrogenation. So a bit of protection, deprotection chemistry from organic chemistry. But what we could do is employ hydrosilylation. Now we haven't done that formally, but someone gave a lecture on hydrosilylation. I think it was, who was it?
Me.
Yes, yes. And we could find a catalyst that selectively hydrosilylates the alkene, and then you could basically do a deprotection and you'd get saturation. Or, okay, that's maybe a bit too complicated. Probably using a poison hydrogenation catalyst would be the easiest. By the way, hereafter we're going to be talking about hydrogenation catalysis in some detail, so we'll learn a bit more about that. So you see, the point is that this is essentially, let's say, a 4-step synthesis to an organic compound, where you really have employed exclusively homogeneous catalysis. Now, in fact, what I could have also done is ask you to synthesize that guy from ethylene. And what you would do is something like a selective ethylene trimerization reaction, right, that we've learned about using the Phillips catalyst, for example. This is a very basic illustration of how you would go about doing this. And remember, the major advantage of many of these catalyst processes that we've learned about is that they have a very high functional group tolerance, right? So it's enormously powerful in organic synthesis. Now, I want to now make a start on our next topic, right, which is hydrogenation. First of all, are there any questions about CC coupling reactions? Oh, before we do that, let's just again review it all. This is from this very nice publication by Nicolau, a very nice review from 2005. I encourage you to have a look at it because it's got some fabulous examples of how CC coupling reactions have been employed in a wide range of natural product synthesis. One of the CC coupling reactions we didn't discuss today is this Trost reaction. Don't worry about that. That's just another variation on the theme. But again, this is sort of what I wrote down earlier, just perhaps represents it in a slightly neater way. It in the end involves coupling, and the variation is always in the transmethylating reagent. Heck is slightly different. And so that I think is a very nice summary of everything we've learned, right? So you must learn to think out the box, right, when you're designing a synthesis, because you have so many tools at your disposal. But the important thing is that, you know, don't forget the fundamentals, right? And the fundamentals are actually quite straightforward, particularly with CC coupling reactions. All right, and now for something different. Now we're going to switch to a new type of catalysis, which is hydrogenation. And this I find very interesting, in fact. Oops, this is my long course. Yes. So today is all about catalytic hydrogenation. Now, in the very first lecture, we discussed hydrogenation, as you might recall. We looked even at a simulation of a heterogeneous catalyst and how it interacts with an alkene and affects hydrogenation reactions through chemisorption. So hydrogenation is a very well-known process, and it works very well with heterogeneous systems. Nickel, for example, radium nickel, palladium/C, and there are many other examples. You can take a great deal of metals, just pressurize it with hydrogen, and have an unsaturated CC double or triple bond, and hydrogen is probably going to add. Now, this on the right here is just to remind you a schematic representation of how the hydrogenation works in the case of a heterogeneous system. And there was that nice video we saw, but essentially it involves some sort of adsorption, chemisorption, remember, perturbation of the CC multiple bond. The hydrogen also undergoes some sort of a chemisorption process and gets activated. You get a Langmuir-Hinshelwood type mechanism generally that results in the saturation of the CC bond. And then step 3 is desorption from the surface. Now, this is employed widely, for example,